Hello children, today we are going to be making a video on Newton's law. So we're going to learn how to approach a Newton's law question, okay? So let's use this question as an example. The question said, using his bakkie, Tiaan pulls a heavy block with a mass of 200 kilograms along a horizontal surface with a force of 400 Newton. The rope he attached to the block makes an angle of 30 degrees with a horizontal, and you have the picture. Okay, 1.1, calculate the frictional force if the block is pulled at constant velocity. Calculate the normal force. 1.3, the magnitude of the new applied force is now 446,2 Newton. Calculate the acceleration. Okay, so when you solve these problems, when you solve Newton's law, problems related to Newton's law, we have steps to follow. So let's go to step 1. Now step 1 is to read. You have to read the question. You have to read the question as many times as you need so you can understand the question. Okay, now this question we're going to read, and at the same time we're going to be getting some information. They say, using his bakkie, Tiaan pulls a heavy block of mass 200 kilograms. So the mass of the block is 200 kilograms along a horizontal surface with a force of 400 Newton. The force that Tiaan applied first is 400 Newton. The force, the rope he attached to the block, makes an angle of 30 degrees with the horizontal. Okay, calculate the frictional force if the block pulls at constant velocity. Important, constant velocity. Calculate friction. 1.2, calculate the normal. 1.3, the magnitude of the new applied force is now 446. New applied force 446,2. Calculate the acceleration. Okay, so that is step 1. We read, and while we're reading, we take as much information as we can from the question. Okay, now step 2 is to sketch the problem, to draw the problem. Now in this question it is drawn already, so we don't have to redraw the question. There is the drawing, so we can just add some information there. The applied force is equal to 400 Newton, and then when the applied force is 400 Newton, then the acceleration is 0. This, how do I know the acceleration is 0? Because the velocity is constant. Okay, the velocity is constant, it's say there, so the acceleration is 0. This is some information that we just add there to the picture. Now step 3. We are going to draw the free body diagram. The free body diagram, very important. Please try to do always the free body diagram, even if it's not part of the question. Even if they don't ask you to do so, just draw the free body diagram. Okay, so now this free body diagram is going to be for question 1.1, because later on the problem changes. Okay, now for this broad free body diagram, I'm going to draw the axis. Now note the following: the x-axis is always going to be parallel to the surface. You can write that note. The x-axis is always going to be parallel to the surface, and the direction in which the object is moving will be taken as positive. So this direction here is positive. Okay, and obvious, the y-axis, you learn in mathematics, the y-axis or the Cartesian plane is always perpendicular to the x-axis. Sorry. So this is my free body, the axis, and I'm going to draw the free body diagram. Okay, now I'm going to start with the forces acting on the object. The first force I'm going to draw is the one I can see clear, which is the applied force, and makes 30 degree angle with the horizontal. So that force will be somewhere there. This is not accurate. You don't have to do it at scale, but you need to know what is going on. This is the applied force. Okay, that is the applied force. What other forces are acting there? Well, there is friction. There is friction. This is a frictional force. There is a weight. There is weight or gravitational force, and there is normal force. This is normal force. Now, when you did vectors, you learned that if the vectors are not right on the axis, you have to determine and find out the components. So this vector have a component in the x direction. This is the component in the x direction and is called applied force in x, sometimes called parallel component of the applied force. I prefer to say applied force in x because I'm using the axis. And if you determine the component of that force in the y-axis, you get here the applied force in the y-axis. All right, that is what we have. Now, what else is known here? This is not part of the diagram, but I'm going to do it anyway. I'm going to show that this angle here, that color is not a good color. Let's get another color that you can see what angle I am talking about. Sorry, let me just get another color. Let's get this one. It's fine. This angle here is going to be 30 degrees. It is given to you in the question. It's 30 degrees. So now we have forces on the x-axis and forces acting on the y-axis. Okay, so we know now the free body diagram. This is very important. So I recommend you to do the free body diagram all the time, even if the question does not ask you to do so. Okay, now, next step 4 is know what law can help us. Step 4, determine the law. Now, up to here, you should have two laws. You learn Newton's first law and you learn Newton's second law. Let's quickly record very quickly the two Newton's law. Okay. Newton's first law. What does Newton's first law state? States that an object will remain in state of rest or moving with constant velocity unless an unbalanced net force act on the object. That, in other words, means that the net force is equal to 0. And when the net force is equal to 0, that means that the object is either at rest or moving with constant velocity. Okay, that is Newton's first law. So when are we going to apply Newton's first law? Whenever the object is at rest or moving with constant velocity. Then we learn about Newton's second law. Newton's second law of motion. Okay, now Newton's second law of motion states that if the net force, which is not equal to 0, acts to an object, then the object will accelerate in the direction of the net force. That acceleration will be directly proportional to the net force and inversely proportional to the mass of the object. So that law in symbols will be something like acceleration is directly proportional to the net force and acceleration is inversely proportional to the mass of the object. Okay, so this is the formula for Newton's second law. When are we going to apply or use this formula of this law? When the object is not at rest or it is not moving at constant velocity. Okay, if it's not at rest and it's not moving at constant velocity. Okay, so for question 1.1, what we said, it is moving at constant velocity. The questions tell you that. So you are going to use Newton's first law. That is the law you are going to use there, because the question telling you that it is moving at constant velocity. Okay, so I am going to start here by writing the Newton first law. Okay, Newton first law. Newton first law. No. Newton first law states that F net is equal to 0. Now I am working in the x-axis because the question asks us to calculate frictional force, and frictional force is in the x-axis. So I'm coming here and I'm going to see what forces do I have in the x-axis. So I'm going to the x-axis, and those are the forces that are on the axis, only those which are frictional force and the applied force in the x, which is a component to the applied force. Remember, we took right as positive, so we have that the applied force in the x-axis minus the frictional force is equal to 0. 0 is the same 0. Okay, so if you rearrange this formula, we have that the frictional force is equal to the applied force in x. Now, if we go here, the applied force in x is this side here. So, using the METs ratios there, we know that the frictional force is equal to applied force multiplied by the cosine of 30 degrees. Okay, and then we can do the calculation. You're supposed to use your calculator, and then you get here 400 multiplied by cosine of 30 degrees. The answer is going to be 346,41 Newton. That is the magnitude of the frictional force. All right, there is the magnitude of the frictional force. Okay, so let's go now to 1.2. Now, question 1.2 asks us to calculate the normal force. We can use the same free body diagram. We don't have to change it. We're going to see what forces do we have on the y-axis. Why with the y-axis? Because the normal force is in the y-axis. So we're going to see what forces do I have here in y. I have normal force, I have the applied force in y, and I have weight. All that is in the y-axis. Now note the following. The object is not moving in the y-axis. So in y-axis, we're still going to apply Newton's first law because the object is not moving and the forces are at equilibrium. So in the y-axis, F net is equal to 0. Now, what forces do we have there? We have a normal, applied force in y, and weight. And we're going to take the upward direction as positive. Okay? So we have normal, plus applied force in the y-axis minus weight equal to 0. If you rearrange this one, you get that normal is equal to weight. This is positive there, sorry. On top is normal plus applied force in y minus weight. So it's weight minus applied force in y. Now, applied force in y, if you go there to the free body diagram, you can see that this is the opposite side. This one here is the same as this one here. Okay, it's the opposite side. So this is going to be weight minus applied force multiplied by sine of 30 degrees. However, we still don't have weight. How do we calculate weight? Weight is equal to mass multiplied by acceleration due to gravity. We are going to substitute it here. Mass multiplied by acceleration due to gravity minus applied force multiplied by sine 30 degree. And then what is left? Well, to do the substitutions, okay? We can do the substitution. We have that the mass is 200. We have that acceleration due to gravity is 9,8. Everything minus the applied force, which is 400 multiplied by sine of 30 degree. And when you do those calculations, which are simple calculations, it's not a problematic one, the final answer for the normal should be 1760 Newton. Okay, that is the value for the normal force. So I hope up until here everything is clear. Let's go to question 1.3. 1.3. Now question 1.3 changed a little bit. They said that the force is now increased to 446,2, and now we do have acceleration. So the free body diagram will be the same, but the only difference is that the applied force in X is going to be a little bit bigger. So it's the same free body diagram. Let's redo it. Y, X, but now this one is going to be a little bit longer. So this is the applied force. We have the friction. We have the weight, and we have the normal force. Remember, the applied force still have to be converted into component. Determine the component there. We have Fa in X, the formula is the same, is Fa multiplied by the cosine of the inclination of the force, angle of the force. Here is the applied force in the y-axis, and this is equal to applied force sine a 30 degree. So it's the same thing, the only difference is that this one is longer than this one now. Okay, but now, what law are we going to apply here? We're going to apply Newton's second law. Why Newton's second law? Because the object is not longer moving at constant velocity. We have to calculate the acceleration. So we are going to apply Newton's second law. Okay, so Newton's second law states that F net is equal to the product of mass and acceleration. Here we are. Okay, in what axis are we going to work? In x-axis. Why? Because the object is moving in the x-axis. It's moving in the horizontal direction. So what forces are there? We have the frictional force and the applied force in the x-axis. So if you substitute there, you have that applied force in x minus frictional force is equal to mass multiplied by acceleration. Note the following. The frictional force will stay the same even though the object now accelerates. Okay? So the applied force is applied force multiplied by cosine of theta minus the frictional force is equal to ma. The applied force is now no longer 400. It is now 446,2. Let's just see it there. It is 446,2. So you are coming here. We substitute everything. It's 446,2 multiplied by the cosine of 30 degree. The frictional force, it was calculated previously. It is here 346,41. 346,41 is going to be equal to the mass, which stays the same, is 200 A. So if you rearrange this one and you calculate, the final answer is going to be 0.2 meters per second square to the right. To the right. All right, and this is all the question. Let's quickly go back and go through the steps. Step 1, when you solve a Newton's law, is to read the question as many times as possible. As long as you don't understand, you have to read the question again. Step 2, you have to draw the problem and write the data of the problem. Step 3, to draw the free body diagram even if the question does not ask. And step 4, you are going to find out, determine what law can we use. We have 2 laws to use here. Newton's first law, when the object is either at rest or the velocity is constant. Or we can use Newton's second law when the object is not at rest and is moving with an acceleration. All right, so I hope this helped you to understand this question. Next time we'll go to a question where we have systems of 2 objects moving together. Okay, thank you very much and good luck.